In this video, we will talk about non-parametric tests. We're not going to talk about all non-parametric tests. There are very many of them and many different variants and formulations. We will only talk about two, the simplest ones that can be used as substitutes for t-tests. What are non-parametric tests? Why do we use the word non-parametric? Because these tests do not depend on parametric assumptions, so assumptions about parameters in the populations that we are sampling. So these are tests that then can be used when the assumptions for the parametric tests do not hold. For example, the most frequently encountered situation is when the assumption of normality is violated. Normality is a prerequisite for running t-tests, and so when our samples are not normally distributed, that is, when we obtain a significant result on the Shapiro-Wilks test, then we cannot use the t-test and have to resort to a non-parametric test instead. These non-parametric tests that we will talk about concern differences between two groups, just like the t-tests. The dependent variable must be measured on at least an ordinal scale. But since we usually use these as replacement for the t-test, the most frequently encountered situation is that the dependent variable is actually a quantitative variable, a numeric variable in other words, therefore at least on an interval scale. However, the non-parametric tests work with ordinal scale dependent variables anyway. The independent variable, like for the t-tests, must be a categorical or quantitative variable with just two levels. That is, our independent variable is a two-group split. These tests do not test a hypothesis about means because there aren't any means. Means require assumptions, and we want to use these tests when assumptions do not hold. Instead, these non-parametric tests test the hypothesis that the two groups are sampled from different distributions, with no reference to population parameters such as means. And there are variants for independent samples and for paired samples. We will only see the simplest of those, and indeed in their simplest possible formulation. You may see different variants in books or online. To understand non-parametric tests, the important concept we need to remember is rank. Because non-parametric tests generally work by replacing the actual measured values with ranks. What is a rank? A rank is the position of a value in a sorted list. So the smallest value gets a rank of 1, and the largest gets a rank of n, where n is how many values you have. Equal values lead to averaged ranks. So they remain equal, but they're still ranks. Let's see with an example how this can work. Imagine we have collected these data, so there are 6 values. Perhaps these are some sort of test scores. The first thing we do is to sort them in ascending order. So the first one is the smallest, the last one is the largest. And then we use this order to replace each value with the corresponding rank. So the smallest value, 50, is replaced with the number 1. The next largest is 53 and 53, and these are replaced with the next two ranks, 2 and 3. And so on up to the largest, the 6th value, which obtains the value, the rank 6. So our ranks range from 1 to the number of values that we have. However, these two values are equal. Therefore, their ranks are averaged. And instead of one having the value of 2 and the other having the value of 3, they both take the value of 2.5, which is the average of 2 and 3. What this does is that you start with a quantitative variable in which distances are important, and you end up with a variable in terms of ranks, which essentially functions as an ordinal scale. Differences are no longer important here. Differences, I mean differences between the original values. So even if this had been 5 instead of 50, so a crazy outlier, it would still be just 1 here. If this weren't 66 but 600, it would still be rank number 6. So the relative distances of these values are irrelevant, and they become treated as an ordinal scale measurement by this rank transformation. This ignores any distortions that may have been introduced in the data by outliers, and it also ignores any deviations from any distribution such as the normal distribution. These issues are no longer relevant. We just get ranks up to the number of data points. Therefore, the only thing that matters from the original data set is the relative position of each measurement. Let's see how that works in actual analyses. The first example will concern independent samples, and we're going to use the familiar situation with vocabulary scores for 15 boys and 15 girls. So these are actual vocabulary raw scores from a receptive vocabulary test. And these are the values for the boys in blue and the values for the girls in purple. To run a non-parametric test on these two groups and test whether the two groups come from different distributions, we first need to convert them to ranks. We do not convert them to ranks by group. Instead, we rank them with the two groups considered together. This is how this works. The smallest of all of these values is 47. So this one becomes rank 1. The next largest is 50, and this gets the rank of 2. Next is 51, which gets a rank of 3. Next is 52, which is actually in the other group. It doesn't matter. There's two 52s, so 4 and 5 would go here, but since they're equal, they both become 4.5. So the average of 4 and 5. The next rank, rank 6, would go to the next largest value, which is 53, but there are actually two 53s, so 6 and 7, and both of these get a rank of 6.5, the average of 6 and 7, and so on up to the top rank of 30, which is taken by the largest value of 91. The important thing here is that ranking is done with the two groups considered together. But the values, the ranks, are still separated by group. So what we can do next is to add up the ranks for one group. So add all these up. The sum of these numbers is 274. And then we subtract from this number, this factor here. So this is the sample size for this group. So the number of boys times the number of boys plus 1 divided by 2. And this results in 154. Alternatively, we could have done this for the girls group, in which case we would have gotten a sum of 191, subtracting this factor for the sample size of the girls, and we would get 71. These numbers are Mann-Whitney U. This is the U statistic. And it doesn't matter which group we work with, because one can be derived from the other. Now, what does this number mean? What is this 154? This seems a little arbitrary and a little complicated because of the extra factor you subtract, but this value actually has a very straightforward meaning. You can obtain this value by counting how many times a boy's score exceeds a girl's score. So if you compare this score with all girls' scores, you will see that it exceeds this value. So 52 is greater than 47, is greater than 51, and is greater than 50. So this exceeds 3 girl values. The same is true of this one. How many values does this one exceed? So how many girl values are less than 60? This is less than 60. This is less than 60, so 2. This is less than 60, so 3. This is less than 60, so 4, 5, 6, 7. So it exceeds 7 values and is equal to 1. So it gets 7.5. Equalities get half a point. And then you do this for every value, and the total number of times each of these values exceeds one of these, plus half of the times there are equalities, is 154. 154 is therefore the number of times a boy value exceeds a girl value, and 71 is the number of times a girl value exceeds a boy value. And these are both corrected for equalities. And now you understand why these two numbers are related. And you can derive one from the other because they cannot be independent. If a value is not exceeded or equal, then it must be greater. So it doesn't matter which one of the two you compute. What does this number mean? How can it be evaluated statistically? Clearly, if one group has values that are greater than the values in the other group, then this is going to be a large number because it will exceed the other group very often. And this will be a small number because it will be often exceeded. In contrast, if the two groups have about the same values, then they will not exceed each other very often, and they will exceed each other about equally often. So this is going to be smaller, this is going to be larger, and they're going to be closer to one another if the groups do not differ. What we need to do to evaluate probabilistically these numbers is to obtain the sampling distribution of U. Of course, there are formulas to do that mathematically, and the statistics programs do that for us. But the most straightforward way conceptually is to obtain a sampling distribution by randomly sampling from groups that aren't different and then calculating U for those groups. Let us try 100,000 random shuffles of these 30 scores, which amounts to random ranking essentially, and this is the sampling distribution of U for two groups of 15. These are U values calculated for sets of two groups, independent groups, that have 15 values each and are randomly ranked, so they're not related. This is the null distribution for U for these group sizes. As you can see, the values 154 and 71 lie symmetrically around the center of this distribution. Of course, because they are related. When one sample exceeds the other more, the other sample will exceed less. So these move in tandem, outwards or inwards. And it turns out that on this sampling distribution, there are about 4.4% of values that are higher than 154 and 4.4% approximately that are 71 or lower. And so in total, the probability that a U value would be as observed or more extreme with groups of this size is approximately 0.088. So that's how you use a sampling distribution to locate the observed value and count the frequency of occurrence of this or more extreme values, which is what the p-value means. How frequently the observed or more extreme indices will be obtained by random sampling. This p-value does not allow us to reject the null hypothesis, which was that the two groups did not differ in vocabulary. Therefore, we cannot conclude that boys and girls have different vocabulary scores at this age. We conclude that there is no difference in vocabulary by sex, or that the variables sex and vocabulary are not associated. Let us now turn to a second example, this time with paired samples. We will use our familiar situation with the 20 children that were administered an intervention, were tested before and after the intervention, and we ask if there is a difference between the before and after scores. How can this be approached? Non-parametrically. So not with a paired samples t-test, but with a non-parametric test for paired samples. Again, we will begin with the before and after scores. So each child here is a row, and the second set of 10 children is here. And for each child, we calculate the difference. What I've done here is I have separated the absolute difference from its sign. So whenever the difference is positive, that is, whenever the after score exceeds the before score, that's a positive difference. 4 minus 3 is 1. So this would be a plus. I don't write anything for a plus. But when this is less, the after score is less than the before score, that is a negative difference. So it's a difference of 2 in absolute terms, and I enter the negative sign here. I'm going to use it, but first I need the absolute value, so how big this difference is. The next step is to rank the differences without sign, so rank the absolute differences. First of all, we throw out all the zero differences. Zero differences do not contribute to a difference between groups. In fact, if all the pairs would be equal before and after, there would be no difference to talk about. Well, then we wouldn't even need to run a test. So zero differences don't count. They're thrown out. And then we rank the rest of the absolute differences. There are actually 9 instances of a difference, of an absolute difference equal to 1 in this case. So 9 times 9 children had an after score that was 1 scaled point higher than their before score. These 9 instances of 1 all receive the average rank. So the average, the mean of 1 through 9 is 5. So all of these receive a rank of 5. And we're up to rank 9. So the next rank should be 10. The 10th value and 2 more values are equal to 2. So there are 3 occurrences of an absolute difference of 2 points. And note that this doesn't count. We're only considering the absolute values. So we have 3 instances of 2-point difference. Ranks 10 through 12 are replaced by their mean of 11. And we're up to rank 12. So rank 13 and 14 concern 2 kids with a 3-point difference. And since these are equal, they both receive the average rank of 13.5. So these are our ranks of the absolute differences corresponding to ranks from 1 to 14. There are 14 non-zero differences here. And there is a minus here. There could have been more in other situations. All we need to do now is take the signs, apply them to the ranks. So all of these ranks will be positive, reflecting the fact that these were positive differences. This rank will be negative, so this will become minus 11. So take on this sign. And then we just add them up with their signs. And it turns out the sum of all of these is 83. And this is the simplest variant for what is called Wilcoxon's W statistic. There are other variants, but this is the simplest one. So our Wilcoxon's W is equal to 83. And then to evaluate that probabilistically, we need to consider the sampling distribution. And the sampling distribution of W for 14 non-zero differences, remember we threw out the 6 zeros, so 14 non-zero differences randomly sampled can result in this distribution of W statistics. This was a simulation with 100,000 samples, simulated samples, randomly drawn to have no difference. As you see, this distribution is symmetric around 0 because depending on which sample you consider to be first and which you consider to be second, in other words, depending on the order in which you subtract them, you may end up with positive or negative differences. And since you take on the signs of the differences into the ranks after you rank the absolute differences, the same amount of difference between the groups could be either a positive or an equal negative number depending on the order of the subtraction. So this ends up being symmetric. And our value of W for 83, which is there, is out at the tails of the distribution. So 83 on the one side minus 83 on the other side, and values of 83 or farther away from 0 on either side add up to almost 0.008. So they're approximately 0.4% on each side with this or a larger sum of signed ranks. This means that we can reject the null hypothesis that the before and after scores come from the same distribution, and we can conclude that there is a statistically significant difference between the before and after scores, not between their means, between their distributions, because this is a non-parametric test. In sum, we use rank-based tests when normality is violated. When we have two independent samples and cannot run an independent samples t-test because of the violation of the normality assumption, we then run what is called a Mann-Whitney rank sum test, which is the first one that we showed here, which provides an index named U, the statistic U, which is equal to the count of times values in one group exceed values in the other group, and we can obtain a p-value based on its sampling distribution accordingly. When we have paired samples and cannot use a paired samples t-test because the normality assumption is violated, then we use what is called a Wilcoxon signed rank test, the simplest variant of which I showed you in the example with the intervention, which provides a W statistic, which is equal to the sum of the signed ranks of the absolute differences, and can look up a p-value on its sampling distribution for the corresponding effective sample size. That is after discarding 0 differences. Both of these tests test the hypothesis that the two samples or the two groups come from different distributions. And we know we have to use one of these when our test of normality is violated. That is, when we get a statistically significant Shapiro-Wilks test.